I also got 1.12.
Okay. Yeah. Now,
Yeah, Connor.
okay.
Sorry.
So if you look at the Nernst equation, and this is just a broad idea, we're going to use this as the basis. E equals E naught minus 0.0592 over n times the log of Q. Now, if you let this reaction run long enough, okay, that's going to be reading 1.12 volts. If you let this reaction run long enough, what's going to happen to the voltage?
It's going to go down
To what?
to 1.10.
0.
It's eventually going to go to 0.
Oh, yeah.
Okay? Okay, it eventually will go to 0. It will lose any potential for these electrons to move.
No
Okay?
more electrons are calling them over for a
Yeah,
party.
everybody's just chilled out, right? So, now let's look at it. This is like a big idea kind of thing, okay? This is a huge, big idea kind of thing. So, at some point, E is going to go to 0. In other words, there will be no reading on the voltmeter. 0.0592, and this is just a generic thing, right, over N. Now, when it reaches equilibrium, instead of Q, what are you going to put?
0. 1. What does that mean?
What do you use, what variable do we use when something's in equilibrium?
Oh, K.
K.
Okay.
KQ.
Wow, that took too long.
K, come on, okay?
Okay.
Okay, literally,
Oh,
it's
we did
K.
the K backwards.
That was backwards for us.
Okay, my bad. So what do I want to, I want to get K by itself. So what am I going to do?
You're going to
Math.
do some subtraction.
Wait, how do
You subtract the E naught,
and
and then you divide by
So-
reciprocal, and then 10.
So let's maybe, so we get a negative E naught over here,
Yeah.
right?
And divide it.
Equals negative 0.0592 over N times the log of K.
Multiply the
So
reciprocal.
we can multiply both sides by negatives.
Yeah.
Yeah, and by the reciprocal.
So how about little E naught N divided by,
0.079.
And then
10 to
put
the
a 10 in there.
equals log of
Okay.
K.
Put it
So then 10 to the
that for me.
E naught N divided by 0.0592 is going to equal
Okay.
K. Now, let's talk about this. Okay? Let's talk about this. Let's play the what if game. Is N ever going to be a negative value?
No.
No. Obviously, the 0.0592 isn't going to be a negative value either. What's the only thing that could be a negative value? E naught. So let's play the what if game. So if E naught is a positive value, okay? If E naught is a positive value, say it's 1, whatever it is, it's a positive value. I'm going to take E naught, I'm going to divide that by 0.0592, divided by a pretty small number, right? So that means this is going to be a big. So let's just look at this. Let's say that, let's do the one that we just did, where E naught was 1.10, right? Okay? So somebody take 10 to the 1.10, N was 2,
So 2.2.
divided by 0.0592, and that's going to equal,
2.2 times 20, so 44.
so we'll take 2.2, divided by 0.0592, and then take 10 and raise it to that power.
1.45 times e to the 37th?
Okay?
Yeah, it's a big.
Oh, 7.
Okay?
What's the units?
Now, there is no units, it's just K.
K.
Oh, that's
Just
annoying.
K.
Now, it's just K. It's okay.
Okay.
It's
Oh,
okay.
it's big K
But it's big K.
for Dylan's.
Now, here's the deal. Here's the deal. Now, this look at this. Okay? Look at Ka values. What do you know about Ka values? Pretty small, pretty big.
Pretty small.
Pretty small.
Probably say pretty small.
So on Ka values that are really, really small, guess what? They don't ionize very much. So it isn't favored in the forward direction. Look at KSP values. What do you know about KSP values?
Small.
They're really small, right? Because those aren't favored in the forward direction because, well, just because of the fact they're not soluble, right? They don't dissolve.
Oh, yeah.
But look at this. Here we have a really, really big K value. We have a positive E naught. Guess what? This is favorable in the forward direction. So anytime you have very big K values, that means it's favored in the forward direction because of the fact that one way to look at this, and you'll see others, but you're going to have a positive E naught value. Now, what if E naught had been a negative value? Well, first off, if E naught is negative, is that going to be a spontaneous or non-spontaneous reaction?
Non-spontaneous.
Non-spontaneous reaction, right? Oh, guess what? K is going to be a really small number. So that's why when you look at K values, you can determine, hey, is this spontaneous or not spontaneous? Remember when we started this discussion with strong acids, right? We said K values, you don't have strong acids for K values for hydrochloric, nitric, that type of thing, because they're really, really big, because they're favored in the forward direction. So when you look at this idea of E naught and this value of K, so basically when you look at this, so K values that are really, really big and bigger than 1, that means those are spontaneous in the forward direction. K values that are much, much less than 1, guess what? They're not spontaneous. And if K equals 1, guess what? That means that the system is exactly in equilibrium. So K values, this is why you look at all the K values that we've studied so far. Ka, Ksp, Kb. Those are small numbers because they aren't favored in the forward direction. Big K values, spontaneous reactions, are favored in the forward direction. Okay? So that's one of the big ideas that you have to get through. Looking at the value of K relative to the value of 1. So let's say that I gave you this problem and said,
Oh, yeah, that's what. Log of 1 is 0.
This kind of looks familiar.
okay, so if I gave you this problem, so basically what would happen, how this would play out, is that you would have a solution of Fe2 plus, which you all have worked with. That's what we did with the titration of potassium permanganate. Okay. How are you going to get the hydronium ions?
I don't know, some acid,
Yeah, dumping some sulfuric acid. Okay. How are you going to get the oxygen?
air.
Yeah, expose it to the air. So whenever you're told that if something is exposed to the air, you're just talking about oxygen. Okay. So what's going to happen to the concentration of the Fe2 plus?
It's going to go down.
It's going to go down, and you're going to produce water, so it's going to become more dilute. What's going to happen to the pH of the solution?
Go down. Because hydroniums are being used.
Yeah, we're decreasing the concentration of the hydronium ions. So basically, we're going to make pure water with some Fe3 plus in it. Okay, that's the short version of what's going to happen. So we need to calculate K. So we're going to use this, and again, don't memorize this. K is going to 10 to the E naught N divided by 0.0592. I will always give you this equation if you need it on the test because it's not on your equation sheet. Okay, but it's one of the most important ones that you need. So what do we have to figure out?
E naught.
Got to figure out E naught, right? So we got to figure out what's being reduced and what's being oxidized. Well, what's happening to the Fe2 plus?
It's losing an electron.
It's turning into Fe3 plus, so that's being oxidized. So that's going to turn into Fe3 plus and an electron. Okay? So what's happening to the oxygen?
Reduced. Is it being reduced?
O2 plus, and this is just on your sheet, right? So you get 2H2O. So what are you going to have? So that reduction potential is, to save you some time, 1.23. And that's negative 0.77. Okay? So this is why we've got to multiply all of these values by 4, right? So we're going to have 4 Fe2 plus, 4 Fe3 plus, and the 4 electrons, okay? So that's, if the equation wasn't already balanced, you'd have to do that, okay? But we already know those numbers. So then you're going to get, what do you get? 0.46. So my K value is going to be a big or small number based upon the E naught value of 0.46.
Bigger.
It's going to be big because I'm going to take 10 and raise it to a positive exponent. So my K would be 10 to the 0.46. N is 4. Divide that by 0.0592, and you're going to get roughly 10 to the 31st. So what that means is that this reaction is very favored in the forward direction. So if I take Fe2 plus, leave it out, put it in an acidic environment, I come back later, it's going to turn into Fe3 plus and water. Okay? Now, if this had been a negative K value, I could have set this stuff out and nothing was ever going to happen to it. Okay? Got that. Now, remember that K could be any number of things. It could be KSP, it could be KA, it could be KB. It just has to be a K value. All right. Now, we have one last set of calculations, and then I'm done. But we need to learn a little bit of electricity.
It's the stuff that's shocking.
It is. So we'll talk about the one we talked about yesterday where we had molten sodium chloride. Let's do molten aluminum chloride. Let's change it up a little bit. Okay. So I'm going to have molten aluminum chloride. So the Al3 plus is going to turn into what?
Aluminum, yeah.
Aluminium.
Al and Cl.
Aluminum. And the Cl minus is going to do what?
Turn it to chloride.
Chlorine gas and
2
2 electrons. Okay, all right. So the overall balanced reaction here is going to be
2 aluminum,
2 Al3 plus plus
6.
6 Cl minus, yielding
2 aluminum.
3 Cl2 plus 2 Al. Okay, so I'm going to be forming aluminum and I'm going to be forming chlorine gas. Okay, so I can make pop cans and then have a poisonous gas. That's a good combination. So when you talk about electricity, one of the things you talk about is current. Okay, and current is shown by the letter I.
Makes sense.
And it's measured in amps. And amps is coulombs per second. Okay? Now, we've talked about like Faraday's constant, which is the amount of charge on a mole of electrons, 96,500. So each electron or proton has the same amount of charge, 1.6 times 10 to the negative 19 coulombs. So if you look at like your house, if you've ever looked at the breaker box in your house, the breakers in your house are rated at amps. Typically they're around 10 to 25 amps. So if you have like a breaker on your house that's 10 amps, what that means is that it can handle up to 10 coulombs per second. If you exceed that, then the breaker throws. It might be 15, it might be 20, it might be 25, okay? So that's what that's breaking on. So the idea of current is kind of like a river. So if you make the analogy that you have like a dam holding back water. So the current is going to be determined by is the size of the opening that allows the water to flow down. So you might have like a very, very, very small straw, and you won't have very much water coming down through there. You might have a big, massive pipe, okay, have that same size, then that's going to allow a lot more water to flow through, and you're going to have a much bigger current. So your voltage is basically, you can think of your voltage as being like the height of the water. So if you have a big voltage, okay, meaning that water is really, really high, but you only have a small straw for that water to flow through, even though you have a tremendous potential for that water to flow, you're not going to flow through very much of it. Now, the other side of it is you might have a really, really big body of water backed up, and then you have this big massive pipe. And then you're going to have high voltage, you have a lot of potential energy stored, and then you're going to allow a lot of that water to flow through because it's going to be going through such a large pipe. Okay? So that's the whole idea. So when you look at this, so here's what we're going to do. What we want to calculate, and this is going to be like one big long stoic problem. Okay? So this is how this plays out. So you got to start with the idea that current is, and this is what's on your equation sheet, current is Q over time, so that's coulombs per second. So here's how these problems play out. Calculate the number of grams of aluminum produced in 1 hour that's a horrible of. Okay, so what we're going to do is we're going to have molten aluminum chloride, and I'm going to run a current through this thing of 10 amps, which means that's 10 coulombs per second. And I'm going to let this thing run for an hour. Okay, so visualize this. I've got this vat of very, very hot aluminum chloride. I've got the electrodes in it. I've got it hooked up to my power source. I know I'm running 10 amps through it. So what I want to know at the end of the hour, how much aluminum am I going to have plated out on the end? So look at this. When you get done, what units is your final answer going to be in?
Grams.
Grams. So I know I want to end up in grams, right? Now, start with this. The 10 amps, what's another way that I could express 10 amps?
Coulombs per second.
Coulombs per second, right? So that means I've got 10 coulombs per second. Now, what else involves time?
The hour.
The hour. So 1 hour is how many seconds?
3,600.
3,600. So let's start with the 3,600 seconds, okay? And I know that based upon my current, that's going to be 10 coulombs per second. Now, if I stop right now, if I don't do anything else, what do I have?
Coulombs.
I have my number of coulombs, right? Okay? That's all I have is a number of coulombs. So here's the question. I got this whole idea of moles, right? Okay? Moles are kind of a cool thing. So what's the relationship that involves coulombs and moles? Faraday's constant. Faraday's constant means that you have 96,500 coulombs per
Joule
mole of electron.
mole, yeah.
So if I come down here and go, oh, 96,500 coulombs, right, per mole of electron, so then I can flip the mole of electron up because it's 96,500 per 1 mole of electrons. So I can flip the 1 mole of electron up here because it's in the denominator of the denominator, right? So now I got 1 mole of electrons. Now, what's the relationship between moles of electrons and moles of aluminum?
3 to 1.
3 to 1. Because if I come back up here, right, Look at this stoich right there. I've got 3 moles of electrons to every 1 mole of aluminum ions, right? That's what that means. So then I can come down here and go, oh, okay, this is kind of cool. I got 3 moles of electrons to every 1 mole of aluminum. Oh, so if I stop right here, I've canceled out seconds, I've canceled out coulombs, I've canceled out moles of electrons. What do I have left? Moles of aluminum. And I know in 1 mole of aluminum that is,
26.98.
so I'll call it 27.0 grams. And if you do this math, I don't remember what you get. I think you get like 3.36.
That's 2 later.
Check that, but I think that's what you got.
Yeah, that's right.
Okay. Now, 3.36 grams isn't that much, okay? I mean, it's like enough to make probably about 3 paper clips out of aluminum, okay? So if you wanted to make more, what would you have to do?
More energy.
More time.
Either run it more time or
More
Increase the
amps.
increase the amps. So if you go from 10 amps to 100 amps,
You'd have 33.
yeah, then you'd have 33.6 grams because then you'd increase that by a factor of 10. Okay? So that's if you want to end up in grams. Now the other thing that you could do is you might get a problem like this. And it's just kind of the opposite. So let's say you want to know how many seconds you would be needed Okay? So now, if you change it up just a little bit, now we're going to work backwards from what we just did. So I know I've got an order to produce 50 grams. Okay? That's how much I want to make. I have a 100 amp current available to me. I want to know how long do I need to let this run so that I end up with 50 grams. So basically, you can do this one of 2 ways. Do you want to start with the 50 grams and then work backwards to time, or do you want to start with the current and work forward?
Start with the grams.
Okay, let's start with the grams. I got 50 grams of magnesium. So what do you think right away, what can I do with the grams of magnesium?
Moles.
So I got 1 mole of, or excuse me, 24.3, that's molar mass of magnesium, right? I think.
Yes, sounds like it.
For 1 mole of magnesium. So I'm going to produce about 2 moles of magnesium. Okay, so now what can I do?
Electrons.
Turn that to electrons.
1 mole of magnesium is
2 moles of it.
2 moles of electrons. How do you know?
Because it takes 2 electrons to.
Yeah, it's Mg2 plus, right? Okay, if it was Mg3 plus, it would be 3 to 1. Okay. Now, how can I get rid of my moles of electrons?
Current.
Prepare day.
1 mole of electron contains
96,000.
500 coulombs, right? Then what?
1 second over 100 coulombs.
1 second over, because I've got a 100 amp current, and if you do the math, you get 3,970 seconds.
You want us to always round seconds with the numbers.
Yeah, just because you only have like 3 significant digits in about everything that you've got. So, got it? Good?
Sure.
Okay, so I'm done. Now, don't flip out, you're only gonna do the ones that are circled on this page, okay? Don't flip
How
out.
does this work?